Welcome to the second session on infinite series. Before I start, happy Pongal to all of you. Happy Lohiri. Okay. And I dedicate this session to our farmers, the people who give us food. Okay. Right. So what I am going to do is I will quickly revise what we did in the last session and get on with the job. Yeah, so this is my YouTube channel. You can download the list of videos of my channel from this site, and this list will give all the videos in a particular topic in order of preference for learning, and it will be periodically updated and uploaded to the same site. If you are a subscriber to my channel, okay, as soon as I upload the new update, I will inform you so that you will come to know. Okay, right. So today's lecture is on infinite series, second session, and on Pongal day this lecture is dedicated to farmers. Okay, so let us get started. So I'll quickly recall. So yesterday what did we do? We had a sequence AN. We assumed the sequence is a sequence in R, but we can also take a sequence of complex numbers if you are comfortable with complex numbers, right? Then what we did was, associated with this we had Sn, which is by definition A1 into AN, which is the nth partial sum. Okay, this is called the nth partial sum of the sequence. Okay, nth partial sum. Okay, once I had this nth partial sum, then I have the so-called a symbol which is summation AN. This is called infinite series associated with the sequence AN, right? Okay, and as I said yesterday, whenever I look at this AN, okay, I actually think of immediately the sequence of partial sums, right? Then I am going to say the infinite series summation AN is convergent if and only if the sequence Sn is convergent. If this happens, we say the sum of the infinite series is yes. We denote this by okay. Notice that even though we say the sum, you should remember there is nothing like addition or anything. You only add finitely many times at any given time. You find Sn, then look at the sequence Sn, and if it converges to S, then you say yes is the sum. Keep that in mind. Okay, don't think of the usual arithmetic. You are just summing and then for you got it. No, for want of better word, we use the word sum, but this is the only way. So as I said in the last lecture, when I look at AN equal to S, I always think of the sequence of partial sums and think of this. Okay, this is the only way you can work with infinite series. Let me repeat, this is what I ended my lecture yesterday in the last session. Okay, right. Now let's look at some special case first. Okay, so suppose AN is a sequence in R with the AN's non-negative. Then let's look at the associated infinite series AN. Okay, then what are Sn? Sn is A1 plus so on AN, but that is same as Sn minus 1 plus AN. and since ans are non-negative, this is greater than or equal to Sn minus 1. Therefore the sequence Sn, the sequence of partial sums, is increasing sequence, right? Okay, therefore if I want to understand when this is convergent, okay, if and only what this sequence Sn is convergent. But what is the sequence Sn? It is an increasing sequence in R, right? Therefore when it is convergent, if only if the sequence is bounded above. Okay, when I am writing this, I am assuming the ends are non-negative. You understand? This is always true independent of an. Whether it's positive, negative or complex number, our definition of an convergence is the sequence of partial sums Sn is convergent. No change in that. You understand? But if ans are non-negative, okay, then I find a pattern in Sn, because Sn's are real numbers, therefore I can compare. I find that Sn's are increasing sequence, and I know from real analysis, or if I watch my lectures on sequences, an increasing sequence of real numbers is convergent if only if it is bounded above. If it is bounded, but any increasing sequence is always bounded below, because S1 will be less than or equal to Sn for all n, therefore S1 will be a lower bound. Okay, that is always guaranteed. Therefore I have to look at Sns are bounded above. Is that clear? So learn this. This is the crux of whatever you want to do. Okay, pause, review, proceed. So let me repeat. Ans are non-negative. I look at the infinite series summation an, and that is convergent if only the sequence of partial sum Sn is bounded above, right? Okay, let us just look at two examples. Yesterday we looked at this in the last lecture. So our ans are r to the power n. Then we found out our s, and look at the associated infinite series, and we found out this is nothing other than, I am also assuming here n greater than or equal to 0. Okay, therefore 1 plus r to the power n, that is 1 minus r to the power n plus 1 by 1 minus r, which is 1 by 1 minus r minus r to the power n plus 1 by 1 minus r, and this is less than or equal to 1 by 1 minus r, because this term is greater than or equal to 0. Therefore, right, therefore Sns are is an increasing sequence and bounded above. Therefore what do I know? This sequence Rn, n greater than or equal to 0, is convergent. But recall, in the last session we found out what is the sum, namely where does Sn converge to. Look at this. This converges to 0, therefore we know it actually converges to S. Okay, this we proved, but today I am just looking at only the infinite series, the so-called geometric series. Okay, for 0 less than or less than 1 is convergent. We know it converges to 1 by 1 minus r, or the sum of the series is 1 by 1 minus r. Okay, right. Now let's look at a second example. Okay, let us look at the sequence an, okay, and the associated infinite series 1 by n. Okay, I have a sequence and this is the associated infinite series. Notice that my ans are greater than 0. Therefore what do I know? I want, so this series summation an, the same as summation 1 by n is convergent if and only if the sequence Sn of partial sums is bounded above, right? So to check whether it's convergent or not, I have to check. Therefore question is the sequence Sn bounded above, right? Okay, this is a small thing. Remember, the student always get confused with the sequence and the series. Okay, this sequence an, which is 1 upon n, that is convergent sequence. Okay, but we are looking at the infinite series summation 1 by n. Okay, that whether I want to know that it's convergent or not. Okay, so let us look at the trick. Okay, so let us look at what is S2 S2 will be 1 plus 1 by half, therefore it's greater than or equal to, let us keep it as it is, 3 by 2 if you want. Okay, let me look at S2 squared, which is S4, that is 1 by 1 plus 2 plus 1 by 3 plus 1 by 4, right? Okay, now what do I know? So each, see, this one is 3 by 2 and this is greater than or equal to, see, 1 by 3 is greater than or equal to 1 by 4, therefore 1 by 4 plus 1 by 4, therefore it's greater than or equal to 3 by 2 plus 2 by 2 squared, that is 3 by 2 plus 1 by 2. Are you convinced? Okay, now let's look at S cubed. Yes, 8. This is 1, 2, 1 by 3 plus 1 by 4. Now I am grouping. Do you understand that? In the finite sum, I can do all tricks of algebra. That is, I can use commutativity, associativity. Therefore, both put together, I can even group them whichever fashion I want. It does not matter. A1 plus 2an, maybe I done with any way. A1 plus A5 plus A7 plus A2 plus A6 plus A3, whatever. It does not matter. So I'm just grouping. So this we know is greater than or equal to 3 by 2, and this is greater than or equal to 1 by 2, and this is what? Each one of them, okay, is greater than or equal to 1 by 8. And how many such terms are there? 4 terms, that is 2 squared terms, and this is 1 by 2 cubed. Therefore, this is greater than or equal to 2 squared by 2 cubed, that is 1 by 2. Right? Therefore, this is greater than or equal to 3 plus 1 plus 1. Okay? 3 by 2 plus 2. So, if you want, you could simply say 3 times 1 by 2. That doesn't matter. Yeah? This is already there, 3 by 1 by 2, but I just want to write it so that life will be easier for me. Are you following? Sure? Okay. Now let's look at what will be S2 to the power n. So how will I do? I will do the same thing. 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 8. Now I want to write down the nth, right? When I wrote 3, look at this, forget this, think of it as a single unit if you want. Okay, so there are 3 groups in this. Here there are 2 groups, 1 group and 2 group, right? And S2 cubed for 3, I have 3 groups. Now what should I, how many groups I should have? N groups I should have, right? So let us look at what will be the last term. How will I find out? See, the last one will be 2 to the power n minus 1. Okay, look at that. So this is 1 by 2 squared, that is 2 to the power 3 minus 1. I stop it, after that I start everything. Are you following? Yeah. So the last thing will be 1 by 2 to the power n minus 1 plus 1 plus 1 by 2 to the power n minus 2 plus 2 plus 1 by 2 to the power n. Okay. Please pay attention. This is very easy. If you are confused, look at the next S2 to the power 4, that starts from 1 by 9. There are 8 terms now, right? So what do I know? So this one is S2n minus 1, therefore I know it is n minus 1 by 2 is greater than, right, by induction. Now let's look at it. How many terms are there? Yes, 2 to the power n minus 2 to the power n minus 1 terms, because the entire term is 2 to the power n. Okay, but up to this 2 to the power n minus 1 terms, so I have to subtract, right? But each of the term will be, each one will be greater than or equal to 1 by 2 to the power n, therefore it is greater than or equal to 2 to the power n. Do all of you get it? Yeah, therefore this is nothing other than n minus 1 by 2 plus 2 to the power n minus 1 and 2 minus 1 by 2 to the power n, therefore it is n minus 1 by 2 plus 1, that is n by 2. Have you understood this? Okay, pause, review, proceed. Have confidence. Okay, this kind of inequalities you should sit and work and pause the video, take a pen and paper, do it on your own. Then only you will feel confident. If you get confused, go back to the video and watch it or to book and then read it again. So what I have shown now, so I want to know whether this is bounded above. Okay, that was the question. What did I find? Let us look at s to the power n. This sequence, think of this as n, okay, for each n, s to power n. Okay, this is a new sequence. And s to power n, this sequence, what do I know? It is each s, for each n, s2 to the power n is greater than or equal to n by 2. Right? So, if this is bounded above, then for all there exists m, so that for all n, Sn will be less than or equal to m. In particular, s2 to the power n should be less than or equal to m. Right? But remember, s2 to the power n is greater than or equal to n by 2. That means n should be less than or equal to 2m. This is true for all n. Okay? This contradicts Archimedean property. Because given m, I can find one natural number so that n times 1 is strictly greater than 2 times m. Yeah? So the contradiction to Archimedean property. Therefore, what I have concluded, so in Sn, okay, I already have a partial, the subsequent, this is not bounded above, and hence I concluded this is not bounded above. Therefore, what is the conclusion? The conclusion is this series 1 by n is not convergent. And if you recall, in the last lecture I say a sequence is divergent if it is not convergent. Okay, nothing to do with infinity, nothing. You understand? Similarly, I say a infinite series is divergent if it is not convergent. Therefore, this is a divergent. That is, it is divergent. Okay, this is called harmonic series. So pause, review, proceed. So I wanted to teach you how to deal with these estimates, inequalities, etc. because many teachers and students are very shy of this kind of thing. If you want to master analysis, okay, analysis, as I keep saying every time, I should be able to compare numbers, functions, behavior, etc. Okay, and I compare the behavior of some unknown function with the behavior of a known function. Okay, this is what analysis is about. So you should be comfortable with looking for upper bound, lower bound, comparison, etc. Okay, is it all right? Okay. Now let's look at another series. Suppose my an is 1 by n into n plus 1 for n greater than or equal to 1. Okay, let's look at the associated infinite series an. I want to know this is convergent, right? So one way you can say is that to find out, look at the partial sums, check whether it is bounded above, right? Because the infinite series are non-negative terms, right? But I'm sure in your higher secondary 11th 12th standard, etc., you must already seen this is a so-called telescopic series. You should learn this. Why it is called telescopic series? You have something, the next thing is inside this, and next thing is inside this, and next thing is inside this, like that. Okay, so they keep on going inside, right? And when I push everything, it comes out only one. So it's something similar. It's a kind of analogy. Okay, let us look at. See, first thing, the moment you see 1 into n plus 1, you know this is nothing other than 1 minus plus 1, because this is the length of the interval, right? Yeah, right. Right, therefore, okay, what is my s1? 1 minus half. What is my s2? Okay, 1 minus half, and plus what is my second term? Here 2 is 1 by 2 minus 1 by 3. Therefore, it is 1 by 2 minus 1 by 3. Right? Now, do you see something very interesting happening? Now, see, I should simply write it as 1 minus 1 by 2 plus half minus 1 by 3 etc. What is a finite sum, so I can group them together, I can do all kind of cancellation etc. Therefore what I get is 1 by 1 minus 3, right? So in general what will be Sn? Sn will be 1 by 1 minus 2 plus 1 by 2 minus 1 by 3 plus 1 by n minus 1 minus 1 by n. So this will cancel with this will cancel with something previous term, so I'll be left with 1 by 1 minus n, right? You follow that? Now Sn's are bounded above by 1 and Sn's are increasing because non-negative, right? And also Sn converges to where? 1. Therefore I know the sum of this series is 1. I hope I did everything correctly. If there is some small mistake, I'm sure you can work it out. Okay. I said when I was doing harmonic series summation 1 upon n, we proved that the set of partial sums, the sequence of partial sums is not bounded above. But I said there is also another easy proof. Okay. We will show that. I will just show that now. Then I will go to comparison test. So we are visiting harmonic series. Again it's essentially the same trick. S1 is 1, S2 is 1 plus half. Let us look at S4, that is 1 plus 2, 1 plus 3 plus 1 plus 4. Alright, okay. And what is Sn? Sn will be 1, 2 plus 1 by 4 plus 1 by n, and S2n will be 1 by n plus 1 by n plus 1 and so on 1 by 2n, right? Now let's look at what is S2n minus Sn. So these things going be there, therefore what I will have will be 1 plus n plus 1 plus 1 by n 2n, right? But notice that each one of the term is greater than or equal to 1 by 2n, and how many such terms are there? N terms are there. Therefore this is greater than or equal to n times 1 by 2n equal to half, right? So what I have shown now? I have shown that for every natural number n, S2n minus Sn is greater than or equal to half. Right? Okay. Now why this is important? Suppose Sn is convergent. Okay. Then Sn is Cauchy. Right? So if I suppose I take epsilon to be anything positive less than half, equal to half is okay, right? Then there exists natural number n in n, so that for all nm greater than or equal to n, mod Sn minus Sm should be less than epsilon, say equal to 1 by 3, right? Therefore in particular what will be S2n minus Sn? Okay, notice that this is positive, therefore this is already greater than or equal to half, but you want that should be less than 1 by 3, right? Because of this should be less than 1 by 3, but we know S2n minus Sn is greater than or equal to half. This is a contradiction. Therefore what is that I will conclude? Sn is not Cauchy and hence not convergent. So in particular it cannot be bounded above, right? Okay, right. Before we go to comparison test, let me just make an observation. If you have gone through my lectures on sequences, you would have seen I proved that if xn is a convergent sequence converging to x, fix a capital N, and up to x1 up to xn capital N, you do anything, you substitute, okay, you just arbitrarily put real numbers y1 y2 y capital N, okay, then the convergence of the sequence is not affected, right? The first n terms are y1 y2 yn, you have no idea what they are, but after that yn, the sequence, the terms will be the original sequence, xn plus 1, xn plus 2, etc, etc. Okay, do you remember that? So what should be the analog of this in the case of series? So that's what we are looking at. Suppose I have sequence an, okay, sorry, a series sequence an and the associated sequence an. Assume this is convergent, right? So in place of an, okay, fix, okay, some integer m and n, okay, let me look at, let these be arbitrary numbers either in R or in C, okay. So if you are uncomfortable, fix to R, no problem, okay. Now I construct a new sequence, Bn equal to an if n is greater than m and equal to Bn. Do you understand what I mean? What I mean is, sorry, I mean this B1 to Bm. After that is am plus 1, an, etc. This keeps the same. So if n is greater than or equal to capital M, sorry, greater than capital M, ak is same as bk is same as ak. So I have a new series, okay, right? I have a new series now. What is that? B1 plus Bm plus am plus 1 plus an and so on. This is my new series summation Bn. The question is, okay, suppose I assume summation an is convergent, the infinite series is convergent. Is this convergent? So based on sequences, whenever I ask this question, many of my students come with the answer, yes, it is convergent and the sum is the original sum. That's not correct. What is correct? Let us find out. Okay, let Sn be the partial sum, the nth partial sum of summation an, and to Tn be the nth partial sum of the series, new series Bn. Now let's try to understand what is the relation between Tn and Sn, right? So for this thing, so let me choose n to be greater than or equal to m plus 1. Okay, you will see the reason, right? Now what will happen? What is my Tn? Tn is B1 plus Bm plus am plus 1 plus an. Is that okay? Right? But I want to know what is the relation between Tn and Sn. What is Sn? Sn will be a1 plus a2 plus am plus 1, right? Therefore this I can rewrite as, okay, a1 plus am plus 1 plus an, okay, plus b1 plus bm, okay, now minus a1 minus a2 minus am. You understand? I added and subtracted, the original things remain the same, right? Now what is the advantage? What is this object now? This object is nothing other than Sn. This object I can group together. This is going to be summation bk minus ak, k equal to 1 to m. So for n greater than or equal to m plus 1, my Tn is this. Do you understand? Now given the sequence, m is fixed, therefore call this as C. This is bk minus ak, k equal to 1 to m. This is a constant now, right? Therefore, the sequence Tn is same as the sequence Sn plus a single constant C, at least for n greater than or equal to n plus 1. Right? Now you use the result. Okay. For sequences, what do I know? The first for finite number of terms do not matter. After that, okay, it's the same. So where does Tn converges to? It will converge to T. I do not know that it converges, but I know Sn converges to S, and C is a constant. This converges to S plus C. Right? Therefore, it follows Tn converges to S plus C. Right? So what do you think I have proved? So the first m terms a1 to am are replaced by some arbitrarily chosen numbers, real or complex. A1, A2, am is replaced by b1, b2, bm. Then I get a new series, b1 plus b2 plus bm plus am plus 1 plus am plus 2 and so on. Okay. So if the original series summation an is convergent, I want to say the new series is also convergent. But the sum may not be the same, but there is a difference. What is that? This one. Okay, therefore summation Bn is nothing other than S plus C. That is, let us rewrite. So B1 plus Bm plus Am plus 1 plus An dot dot dot. This is same as summation An n plus summation Bk minus Ak k equal to 1 to n. Okay, pause, review, proceed. Yeah, okay. For example, we have seen if an is 0 for all n, this series is convergent and its sum is 0. But suppose I make a1 equal to 1, all n equal to 0 for n greater than or equal to 2, then what will I get? 1 plus 0 plus 0. Right? Therefore, the sum of this series will be 1. Right? So you should not expect, okay, if the finite number of terms of a convergent series are changed, the convergence is not affected, but the sum may be affected. Okay. So now let's come back to the most important result in our comparison theorem. Notice this is only for positive terms. Positive, by positive I mean non-negative. So let us look at a finite thing. Suppose I have finite numbers a1 to an and b1 to bn. Assume each a is less than or equal to bi. Then what do I know about the relation between this finite sum? I know they are less than or equal to. Right? So this is a basic thing. This is for finite. Is there any assumption about sign? My a's or b's should be positive, negative? Nothing. They are finite set of real numbers or complex numbers. You understand that? Notice that no assumption. On an and a case or b case. A case or b case. K equal to 1 to n. Right? Are you following? Yeah. So these are all real numbers. Sorry, because I want to say less than or equal to. So a1, a2 and real numbers, b1, b2 are real numbers, so that a is less than or equal to bi. Because complex numbers I can't say less than or equal to. I do not know whether I said, maybe I said complex, that's why I'm going back. Okay. So a1 plus a2 plus an will always less than or equal to b1 plus b2 plus bn. Yeah. Okay. Now I can ask a similar question. What I can ask, suppose I have sequence an of real numbers and sequence bn real numbers. Let us look at the associated series here. Okay, such that an is less than or equal to bn for all n. Okay, then what can I ask for? I can ask for either whether there is any relation between this. Right, notice that. Okay, when I want to say this as, then I have to assume these are convergent, then only it will make sense. Okay, first thing is, okay, is there any relation between is that question clear? Let's go slow. I want you to understand this thing properly. Right, suppose my ans are, let us say, minus 1 for all n, and bns are 0 all the time. Right, then an is less than or equal to bn. But what do I know about let Sn be the partial sums of summation an and Tn partial sums of summation Bn. Then Sn is minus n and Tn is 0. Right? Now what do I know about Sn? Sn's are on the sequence. Sn is unbounded. Therefore this series is not even convergent, whereas this series is convergent. You follow that? So I cannot make any kind of kind of comparison. Of course you will say the minus infinity is less than or equal to 0, but we don't want to do that. Okay, so the result is the comparison test. Let's assume an and bns are sequences of non-negative real numbers. Okay, let this and this be the associated infinite series. Assume that for all n, let's say assume there exists n in n, so that for all n greater than or equal to n, an is less than or equal to bn. So I do not know what happens up to a1 to capital A capital N, and similarly b1 b capital N. I do not know, but after that I know. Or if you want n minus 1. Okay, let's not worry about such things. Is that okay? So a1 an minus 1 b1 bn minus 1. I do not know what happens here, but I know here. Okay, this is what I know. From here onwards I know that. Okay, now what do you think I want to say? I want to say that summation, suppose summation bn is convergent. If summation bn is convergent, so is summation an, and summation an, the sum is less than or equal to the sum b. Not only it is convergent, the sum of the infinite series summation an will be less than or equal to sum of the infinite series summation bm. Okay, is that clear? Okay, so let us prove it. There should be something to do adding page. I always keep forgetting. And I don't want, I want it to be right. Okay, so let Sn be partial sum of summation an and Tn, the nth partial sum summation Bn. Now okay, let us assume n is greater than or equal to capital N. Okay, now notice that because of what I said, the first n terms do not matter for the convergence. Right? Yeah, but this may not be true. Okay, this may not be true in general if I put this condition. I'm sorry for that goof. I'll tell you why. Yeah. So this is not true under this condition. So let me rewrite. So let us assume for each n, an is greater than or equal to 0, bn is greater than or equal to 0, an is less than or equal to bn. Okay. Then assume, okay, this is the first thing. Assume summation bn is convergent. Then summation an is convergent and summation an is less than or equal to summation bn. Okay, now I am assuming for every n. Okay, I will come back to what happens if I remove finite things. Convergence will remain the same, but what the sum may not be, you may not be able to compare. Very trivial example I will give, don't worry, I'll come to that. Okay, right. Now let us look at, so why, so let Sn be the nth partial sum of summation an and Tn nth partial sum of summation bn. Right? Then what is Sn? Sn is a1 plus an. But remember, for each n, a1 is less than or equal to b1, a2 is less than or equal to b2, and an is less than or equal to bn, therefore is less than or equal to tn. Right? Therefore, what I have found? I have found that for every n, okay, Sn is less than or equal to tn. Yeah? Right. Now, this hypothesis summation bn is convergent. And remember, bn's are non-negative. Therefore, what do I know about Tn? Tn is an increasing function. Therefore, when I say this is convergent, what does it say about Tn? Tn's are bounded above. And Tn converges to T. What is T? That is LEB of Tn's. Right? Therefore, what do I know? Tn is always less than or equal to T for all n. But what do I know? Sn is less than or equal to Tn for all n. But Tn is less than or equal to T for all T for all n. Therefore, Sn is less than or equal to T for all n. That means the sequence Sn is bounded above. And again, since ans are non-negative, Sn is an increasing sequence and bounded above. Therefore, what do I know about that? Therefore, Sn converges to S, where S is the LEB of Sn n in n. Okay, right. Therefore, I have proved, that means summation an is convergent. So this is proved. Next, what I have to show? The sum summation an is less than or equal to the sum summation bn. Okay. Now what does that mean? What is summation an? Remember, whenever I write this summation an, what does it stand for? It stands for S, where S is the limit of the partial sum Sn. But in this case, it is LEB of Sn. Correct? Yeah. Therefore, now, therefore, for each n, Sn is an upper bound for this set. Okay? S is an upper bound. It's a least upper bound. So, S is LEB of Sn as n varies over n. Right? This is nothing other than your sum. This is our definition of sum. Okay? As I said, this is just a symbol. It stands for only limit of Sn. In this case, limit of Sn turns out to be LEB of Sn. Right? But remember, we know each Sn is less than or equal to Tn, and hence T. Therefore, T is an upper bound for the set Sn. And S is the least upper bound. Therefore, what is the relation between S and T? Therefore, S must be less than or equal to T. But what is S? This is the notation This is the sum of the infinite series. This is sum of the infinite series Bn. Therefore, we proved this. Yeah, you accept it? Okay. Now let's go back to the thing why I said I have to be a little careful. Suppose I take my an equal to 0 for all n. Okay, let us say an equal to 1, okay, for 1 less than or equal to n less than or equal to 10, 0. And let's take bn to be 0 for all n, right? Then for n greater than or equal to 11, my an is less than or equal to bn. And we know summation bn is convergent. Okay, and what is summation bn? That also we know it is 0, right? Can I conclude summation an is convergent? I can conclude because I would only change the finite number of terms up to 10 terms, but then the summation an is going to be 10, right? Because what will be S10 will be 10, S11 will be 10 again, because A1 plus A2 plus A10 plus A11 and so on. You understand? Therefore, it's going to be eventually a constant sequence after the 10th term onwards. Therefore, it will be 1. Sorry, 10. Where this is. Even though it is convergence is correct, I cannot conclude less than or equal to. Okay. Are you following? Yeah. So, what is that next I want then? So, let a modified version which doesn't say about the sum. Okay, assume that there exists. So an's, okay, are non-negative, bn's are non-negative, okay, and there exists n such that an is less than or equal to bn for all n greater than or equal to n. Okay, and assume that summation bn is convergent. Then summation an is convergent. Okay, are you following? Yeah. The way I do that will be, let us say a for n greater than or equal to capital N, my a1 to an plus an plus 1 plus an. Okay, I can say this is going to be, I can do the same kind of thing, right? Okay, these fellows will be less than or equal to a1 plus an plus bn plus 1 plus bn. Yeah, so but this I can again write as, okay, add and subtract. So b1 up to bn minus 1 you add, or bn up to that you add, I don't care. Okay, and bn plus 1 to bn. Okay, but these terms should be there and these terms are extra, so I will do the same thing. What do I do? Summation k equal to 1 to n ak minus bk. Now this is a finite sum, right? And you call this as a Sn, you call this as Tn. Therefore Sn is what? Tn plus c, right? You follow that? Okay, so what do I know? Now this is bounded by t plus c. Suppose, what am I assuming? I am assuming Tn is bounded above because Tn's are increasing, okay, and summation Bn is convergent. That means Tn is increasing sequence bounded above. Okay, let t equal to LEB of Tn. Okay, therefore what I have is Sn is less than or equal to Tn plus c, but that's less than or equal to t plus c, right? This is true for all n. Therefore Sn's are bounded above. right? And Sn's are increasing. Yes, right? What is that? We know, because Sn's are a1 plus a2 plus an's are non-negative. Therefore Sn is an increasing sequence, and it's bounded above by t plus e. Therefore the sequence Sn is an increasing sequence bounded above by some constant. Therefore it must be convergent. That means summation an is convergent. Okay, please go through this argument. These arguments are usually not done in detail, because I wanted to impress upon you the only way to deal with infinite series is, you know what to say, right? Summation an, I want to say something. What should I look for at? I should look at the sequence of partial sums Sn, okay, and deal with it. I should try to answer anything with infinite series by means of this. That is what you should learn. If you go through my lectures, if you learn that much, that's it. I'm very happy. So we will meet again. Take care. Stay safe.